So in the previous session, we have looked into the execution of a software program, right, rather written in machine code on our CPU, right? And we had an idea about the different instructions that were available for our architecture or our microarchitecture implementation that we sort of showed you, and those were being used to implement very simple programs. And for example, we have showed you an application where we added and subtracted a few numbers, and the result was available after the computation was over in a register that we displayed, right? And today we are going to look into the detailed implementation of some of them, in particular the control logic. So revise the last session just to be kind of aware of the kind of registers that we have, how the ALU is connected to the bus, and the other different special purpose registers like memory address register, the instruction register, instruction program counter, and so on, right? So by now we should have a very good idea about how they are placed and connected with the various other components, and how the overall microarchitecture of our CPU that implements our ISA looks like, right? Although I keep on saying ISA, it is something very trivial and very simple for us, right? We have defined only a few, very few instructions, like 8 instructions or so, but that should give you an essence of how instruction sets look like. Of course, it has to be complete. It needs to be able to perform various kinds of computational jobs, right? Otherwise your instruction set architecture is not going to be called complete, or something called Turing complete. I'm not going to go into the details of Turing completeness, but you can think of any computation that could be reduced into instructions that are satisfied by our instruction set architecture. For example, even if multiplication instruction is not available in our ISA, you provide a for if you provide an add instruction, and you provide some mechanism to repeat things over a period of time, let's say like a for loop, right? So jump instruction in our case, or let's say jump with some condition like j in z, j c, and so on. That should be able to we should be able to realize a multiplication functionality using those instructions, right? So there could be other things also, and there is no end to it, right? How complicated functionality you want, and often you want to reduce that into blocks of very simple functionalities, and there is always a trade-off in between them, right? So again, recapping our architecture, in our architecture we assumed a few instructions. If you concentrate on the left hand side of the screen, typically the first 8, right? This is something that we have already seen how it can be implemented, and I am going to give you a little bit more details about how to actually implement this in our control hardware. So NOP, LDA, STA, these are the load and store instructions for the accumulator, from the accumulator to the memory, or from the memory to the accumulator. Addition and subtraction are also memory operations. Load I, LDI is basically a load immediate, jump, and instead of swap, I think what we used was out in our actual implementation, where the content of register A was transferred to register C, and it was displayed in some 7 segment LEDs, right? And we kind of looked into simple micro or simple machine code, right, that was using these instructions and executing code, right? And we also looked into the control logic for implementing each one of these instructions. We are going to show you the exact implementation today, right, so that you can also implement it much more efficiently. So by now you know how exactly this control logic works, right? So if you remember, we basically take a few bits from the opcode, which instruction it is going to be. We take the bits from the t state counter, and then use that as an address for our software control ROM logic, right? And in that address, whatever is our data, that data is our control word or our micro instruction. So And how do you create these micro instructions? An easy way to do this or realize these micro instructions in software is using this kind of code that I have shown here. For example, for doing the fetch cycle, so if you see, this is our fetch cycle and the first two micro instructions. So one left shift PC out is going to shift 1 by the value of PC out, and the value of PC out is probably 14 or 13, depends on this value here, right? Or bitwise, or one left shift MAR in, right? So these are the two bits in the 16-bit vector that has to be turned on, right? Or that has to be 1, right? So in this way, you can keep on creating the 16-bit vectors based on your requirements for the particular instruction. Okay. So we will look into a running program that is going to do this and create the control words for loading inside a EEPROM, right? Or any kind of a ROM that is going to be used for the control logic, right? Remember, this is software control logic. This is not a hardware control logic, because for a hardware control logic, you need to come up with a circuit for all the different control bits or the control outputs and the inputs being the opcodes of the bits of the opcode and the bits of the T state counter. Okay, T state counter or the ring counter, whatever you want to call that. So, and this is what from a software control ROM perspective, right? This is what exactly your control ROM should look like, or these are the contents of the control ROM. As you can understand that if you make even a single mistake, right, in one bit, this is in hexadecimal, and the actual thing is done in single individual bits, right, and that has been encoded in hexadecimal format, right? So in any one of this, right, let's say we can take one particular example, and we went through this 4600, right? Why it is 4600? So 4600 is 4 sets of 4 bits, right? So 4 is going to be represented as 0100, then 6 is going to be represented as 0110, and then the two zeros are 0000 and 0000. So each one of this control word or a micro instruction is 16 bits long. Okay, so there are 16 bits or a 16-bit vector, right? And all the 16 bits are meaning. For us, I think we have only 15 control bits. So the 16th control bit or the most significant bit could be assumed to be 0. Okay, unless and until otherwise specified, it could simply be 0. Okay, now let us look at creating these control words automatically or programmatically. I won't say automatically, programmatically. Okay. So I will show you a sample C program. You can always write this in Python or any other language that you are comfortable in. So let us go through this thing one by one. So this is the variables that I have declared, and each such variable is assigned to some this bit position, right? So PC increment is the 15th bit. If you take it from 0, right, 0 index, so it is actually written as 14, but this is the most significant, I mean the second most significant bit in the control word, the most significant bit being 0, right? So unsigned int PCINC equal to 14. Then we have 3 more. So for dedicated for the program counter, the others being PC out. So the PC out, as you can recapitulate, writes the value of the address to the bus, right? PC load is if you want to load the PC, because the PC is the program counter and you might require the program counter to be loaded by some value, and that value has to be supplied by the bus. Okay, so these are the 3 control knobs of the program counter. Next we come to the memory module, because your CPU is going to talk to a memory. For us, we have a very simplistic memory. So remember that we are not using any memory data register or memory buffer register. We are directly inputting and outputting to the memory here, right? So memory in is you are reading from the bus to the memory. So you are trying to write to the memory rather. right, which is the 11th is basically equal to 11, and memory out is you are reading from memory. So the memory is trying to write its contents to the bus. Okay, so memory out equal to 10, and then you have instruction register in out, you have memory address register in. Note that the memory address register does not have a out because the output of the memory address register is directly fed to the memory for a lookup, right? Memory address register is never going to write to the bus. Okay, I mean, at least in this kind of an architecture, there is no such requirement. We don't want to waste a control word for that. It is never going to be used. So our architecture is the memory address register's output is directly connected to the address input of the memory. Okay, so and then we have let me kind of partition it out, right? We have memory, there is instruction register in out, memory address register, then we have the what is called a register file. So REGA is register A, REGB is register B, and so on. So we have 3 registers, and 3 registers in and out pins are also there. So sometimes some combinations will be needed, right? So who is going to be turned on, who is going to be turned off, and so on. You can optimize this. For example, if you have let's say 5 registers or let's say 8 registers, you can, who is creating the output, you can be actually using just 3 bits instead of 8 bits, right? So if you have 8 registers in the register file, only one register can be set as the broadcaster, right, or basically outputting to the bus. Who is outputting to the bus? We know that only one register can output to the bus, right? So basically you can choose that using some decoder, right? So that could be a better way to save some bits, right? Whereas in case of our inputs, right, if we have the restriction that only one register is going to be reading from the bus, then you can use 3 bits, right? So then if you have 8 registers, so 3 is going to be used for selecting one of them, and if you just say that only one register is going to be reading from the bus, then you need 3 bits for selecting the input register. For output register, definitely you need 3 bits. So if you ask the question that how many bits at the minimum are required for the control lines, if you have 8 registers, right, without any optimization, the answer would be 8 plus 8 equal to 16, right? 8 registers you want to set ones or zeros for selecting the inputs, and for the output you can use 1 bit, definitely only 1 bit has to be on, but you are, without any optimization, you are wasting like 8 bits, right? That can become 3 plus 3 equal to 6 given the restriction that you want to write only one register is going to be reading from the bus. If you do not have that restriction, then you need 8 bits to select one of them, multiple ones of them. So in that case, it is going to be 8 plus 3, 11, because for outputting you only require 3 bits. There is no multi-register output possible in the bus. Okay, so keep these minor things in your mind. Here we have not done any optimization. There are 3 registers with 2 control inputs, so 3 into 2 equal to 6. And these are the control bit indices, right, in the vector. So starting from 1 to 6, these are your register C out through register A in. And then we have one more bit for the ALU. The ALU also does this computation and so on. We want to control when the ALU's results are going to be available in the bus. We can make it explicitly available based on the instruction that we design. Maybe in our case, for addition and subtraction, we explicitly mentioned that after the addition is done, the result of the addition, right, the result is going to be available in register A. Okay, so in that case, the ALU has to keep the output flag on, right? The output has to be on, and then that is going to enable the output to be available in the bus. Okay, and we can also simultaneously make the register A listen to the bus. So the output from the ALU is going to be transferred to the bus, and from the bus it is going to be transferred to register A. Okay, so ALU input is not necessary. As you can see, ALU input in our architecture, it's already directly connected to two registers A and B. If you had an option, then of course you need to choose some kind of a multiplexer to know which registers from the register file is going to be used for ALU input, right? That's a separate discussion. In the control logic, we do not have anything like that, because we are not choosing any registers to be connected to the ALU for the inputs. It is always A and B. Okay. So for any computation to take place in the combinational circuit that the ALU has, you have to make sure that A and B are loaded with appropriate values that you want to make your computation on, right? Okay. So this was basically the definition of our control word vector, right? So these are the different bits in your micro instruction. You can reorder it, or you can do it according to your micro architecture. This is a very simplistic and very limited in terms of functionality. We only have 15 bits. Real life control words can be having 50-60 bits. Okay, even more than that, right? It could be pretty much complicated. Okay. As your number of components, as you can understand, right, the number of components increase every component has to be given some kind of a control input, right? And if you have things like pipelining and so on, this is going to increase. Okay, so this is a CPU that is executed. It's called a multi-cycle processor. Every instruction is going to be executed in few clock cycles. Okay, and every clock cycle we are going to you are going to introduce one micro instruction to the processor, so that micro instruction gets executed. So now let us try to see. This is a partial code that I have already said. I have done it for a few instructions. You can complete it for your instruction set. So I have 5 instructions, and we assume, based on whatever we have studied so far, addition and subtraction was using 5 T states or 5 machine cycles. Let us not use the word machine cycle. I will use the word clock cycles. Okay, so 5 T states or 5 clock cycles. However, if you want to look up the ROM in this format, we need this 4-bit instruction, that is our address, right? A 4-bit instruction or the opcode and the 3-bit T state value. So we have 7 bits, right? So the 7 bits can actually look up 128 different addresses, and since we only have 5 T states that are valid for a given operation or a given opcode, so we have to ignore the last 3 entries, right? Because if you look at the structure, this is the address, right? 4 bits, comma 3 bits, totally 7 bits, right? So if you concentrate on the last 3 bits, 000, 001, 010, 011, 100. These are the 5 T states that are valid. However, 101, 110 and 111, 5, 6 and 7 are not needed, right? So we can just simply fill them with zeros. Okay, so they are not going to be needed, but we have to skip those values anyway and then start the next instructions data. Okay, so I have shown an example of the memory layout for an instruction. Let's say the operation is 1010, right? 1010 is your opcode. So you have in the memory you have the previous instruction, the previous, I would rather say previous micro instruction, right? And this is the next micro instruction. So the previous micro instruction is going to be the last micro instruction for 1001, right? So this is previous micro instruction for instruction 1001. So that is 9. Okay, so 9, after that this is 10, right? 1010 is 10. Okay, so 1010 is the first 4 bits that is going to specify the most significant 4 bits of the address, right? Remember, this is not the data, this is the address by which we are going to look up the ROM. Okay, then you will basically have 000, 001 and so on. So this becomes contiguous set of memory. So this starts from 101000 to 1010111. So there are these 8 locations. Out of those 8 locations, the first 2 locations or the first 2 micro instructions are going to be the memory, are going to be the control words for the fetch cycle, right? Fetch 1 and fetch 2, because there were 2 things that we were doing. One was from the PC we are outputting to the bus, and from there we are going to read it to the memory address register. That was the first part. Later what we were doing is memory output was enabled and we were loading that thing inside the instruction register, as well as in parallel we were updating the program counter or incrementing the program counter by 1, or depending on the size of your instruction, how much you want to increment the program counter by how many bytes. Okay, so these were the first 2 micro instructions, and that is going to contain be contained in the first 2 memory locations. After that, depending on your instruction, you have to do some work, right? The actual stuff is basically the real work that that instruction is going to do. If it is an add, it is going to do something else. If it is an LDI, it is going to do something else. If it is an LDA, it is going to do something else. So those are the actual instruction, micro instructions, right? And after that, we pad this area with 0. It's not necessary. I mean, after 100, given that your T state counter or your ring counter is going to go back to the 0th state, right? It counts from 0, 1, 2, 3, 4. After that, it does not go to 5, it goes to 0 again, right? So your ring counter might simply cycle through only these states, but you cannot start putting the next micro instruction from this place, right? Because this address will be something else, right? It is not going to be aligning to your instruction comma T state value logic, right? So you have to skip them, right? And then start the next micro instruction for the instruction 1011. So 11, right? So you start it for the next one. Then you are going to have again 8 more such entries, right? 8 more bytes, right? Not bytes, these are all 16-bit control words, so 2 bytes long. So here it is 2 bytes, okay? And if you do not have anything to do in a machine cycle, we pad it with 0, right? So these are zeros. So these are basically garbage, or this is not something that is going to be used by the processor, right? If you accidentally have a counter that is not being used as a ring counter, let's say you are having a regular counter, right? The regular counter maybe just starts from 000 and goes on till 111. In that case, you need to be very careful. You have to be putting zeros here, right? Otherwise, it will accidentally, you will get unanticipated results if you have garbage, right? Because whatever you have here is going to be actually executed by the CPU, okay? So the better, I mean, that is not a very smart idea to have a regular counter here, because these 3 control words are really not necessary for any of the instructions, right? If you remember, I told you about 3 levels, right? The naive thing is just to have a counter that counts from 0 to 7. So if you count from 0 to 7, every instruction is going to take 8 clock cycles. And I know that none of my instructions are more than 5 clock cycles. Then that is definitely a stupid thing to do, right? So one thing that we can do to make it better is to have a ring counter that starts only from 0 and always cycles through 5 states, right? At least that saves you 3 states, right? So 5, 6 and 7, these are never touched by the processor, right? So that is the control logic. If the previous one was 1.0, this is 1.1, right? At least a little bit better. So you will always go from 0, 1, 2, 3, 4 again back to 0. So what was the problem with that? I mean, that is apparently not an issue. I mean, definitely we are also doing the same thing. Then we can do a 1.2 version of the control logic. If you realize, not all instructions are going to have this actual stuff 1, actual stuff 2 and actual stuff 3. Some instructions might only have 2 micro instructions, right? For example, let's say LDI, right? LDI might not need all 3 micro instructions, right? Maybe probably done with just 1, right? it's an immediate load, right? The only thing that it is going to do is that take that value from the instruction register and load it to the accumulator, done, right? So it is only going to have only one actual stuff kind of a sentence that I have written here, right? So 2 and 3 are not going to be used. So what you can do is an additional intelligence that you can give to the counter is that based on the instruction you can reset the counter at different point in time. Of course that is going to require you much more elaborate circuit, but there is something that can be done. So you don't have to waste these 2 cycles for instructions that don't need them. Okay, so if you think of add or subtract in our example, this is going to take all the 5. But if you think of LDI, this is only going to take these 3, right, and nothing else. Okay, so our implementation here is pretty naive. We assume that it can go from 0 to 7, and these 3 are all zeros, at least in the memory. That is why we have to write it like this, right? The counter, it is independent of the counter. The counter can either grow from 0 to 7. In that case, this is going to be ignored or being treated as NOP. So this is going to be treated as no operation or NOP in case the counter creates a T state equal to 101, 110 or 111, in case. Otherwise, even if it is a smarter counter and it goes from 000 to 100 only, that is also fine for us. Okay, currently what we are doing is the ROM programming. Okay, so now let us look at these control words. I have defined an array because you are basically going to have 16-bit micro instructions, 8 per instruction, right? So 8 per instruction, and you are going to, let's say, going to do it for 8 such instructions, right? So 8 instruction multiplied by 8 micro instructions per instruction, right? So you are going to have 64 such entries. Okay, so I have done it for 1 2 3 4 5 instructions. So if I do it for 5 instruction, every instruction has 8 micro instructions, so it is going to be having 40 micro instructions. 40 micro instructions is 80 bytes. Okay, every micro instruction is 2 bytes, right? 16 bits. Okay, so here what I am trying to do is the first micro instruction is one left shift PC out, or one left shift MAR in, and this is basically your second line of the fetch cycle, right? You increment the program counter, memory output is enabled, instruction register in is enabled, everything else are 0. Okay, so how many zeros are there? There are 6 zeros, 0 0 0 0 0 0, right? And this is NOP. So I basically say that this is my NOP instruction, and the 4 significant bits, the 4 most significant bits for NOP, or basically your operation for NOP is 0 0 0 0. These are the 4 significant bits for the address of the software control ROM. So these are the first 4 bits. Then the 3-bit T state will come. So this 0 0 0 0 0 0 0, after that 3 bits will be there, right? So this is going to represent this location. Whereas 0 0 0 0 1 1 1, that is the last micro instruction, is going to be representing this, right? The last 0. So this entire thing, right, are basically 8 micro instructions. This is the first micro instruction, second micro instruction, third, fourth, fifth, sixth, seventh and eighth are all zeros. Okay, so let us look at the more useful micro instruction. Here it is LDA. Okay, don't think it is LDA 0001. LDA's machine code is 0001. Okay, so LDA's machine code is 0001, which is basically your opcode for this instruction. So your address, if you look at the previous one, the last zero's address was 0000111. Okay, what will be the next address? The next address has to be 0001. So this NOP last, I'll write UINS. UINS stands for micro instruction. Okay, so the last micro instruction address is 0000. Then I'm putting a dash just to segregate the opcode part with the T state part, right? There is no real dash. Okay, so 00001111. What will be the next address? The next address is going to be the first micro instructions address for the next instruction. Okay, so here the first micro instruction address is 0001 000, right, 000. If you can see that this is basically 7 and this is 8. Okay, if you remove this dash, because this is just for our understanding, after 7 the next one is definitely 8, right? But we have the first micro instruction of the opcode 0001. Similarly, the last is 0001, because that is our opcode. 111 is your T state, right? So if you look at in this way, in a partition format, it is easier for us to understand. So this is basically 8 to 15, right? Again, this is the next one is going to be 16 to 8, right? So 16 to 24. Okay, so this is how it is going to continue, right? So this one is going to start from 0010, and then after this 000 to end one is 001011. Okay, so this is 16 plus 7, 23, right? And this starts from 16. So 16 to 23. The next one will start from 24. Okay, so this you can see that this is basically an array. Okay, so this is, you notice this commas, right? So you basically have 8 values, then you have 8 values, then you have 8 values. It's very easy for us to write in this format rather than directly writing the binary value. It becomes very hectic, right? So you define the control words in this format. You can have more, right? So this is we have here is the NOP, LDA, STA, add and sub, right? You can also do LDI. So if you want to do LDI, you have to write something more here, right? So then it is going to issue the LDI commands. And after that, we basically print them out. This is not necessary, and if you directly program the ROM, here we want to use a simulator. So the simulator, I need to copy and paste the ROM outputs, right? So if you run this program, you can see these are our control outputs. Okay, and this could be loaded in my EEPROM. So if you look at our EEPROM, this is a circuit, it is basically a module like this, right? Hope you can see this. And on the right hand side, there are two things. One is the address width. Address width basically means how many locations you can address. Okay, in our case, let us say in our case, we want to support for 8 instructions, and each instruction having 8 micro instructions, right? So 64, right? So you can either provision it for the first 3 bits, or we have already decided that we are going to use the first 4 bits of the 4-bit instruction, right? So if you are using 3 bits for the instruction, then it becomes 8 instructions. But if you are using 4 bit for the instruction, it is 16. You are provisioning for 16 instructions. So 16 multiplied by 8, it's going to be 128. Or you can see here we have already defined these are 7-bit addresses. Okay, so you can say that my address bus width is 7 bits. Okay, so it has immediately become 128 bytes. Okay, and why it is 128 bytes? Because every location is programmed to have only 1 byte, but we need 2 bytes, so that is the bit width. So we can always say the bit width is 16. So you can see 128 multiplied by 16b. So 128 locations, so 128 micro instructions. Every micro instruction is going to have a 16-bit vector, right? And we know what that 16-bit means, right? So the output here we can see every such output, every such individual output is nothing but 16-bit values. Okay, you can directly take that and paste it here. So you can actually, this simulator is nice. You can double click this and you can paste the values. Okay, so let us see. Let us try to do that, right? I think I have given a new line. So the new line, the simulator might not like this new line. So this is going to be a one contiguous output, right? And let us load this. Hopefully there is no issue. Yeah, so 40 cells loaded. Why 40? Because we had 5 micro instructions, 5 instructions, and each instruction having 8 micro instructions. So 5 into 8 is 40. So now this is loaded, right? So what we can do, we have to read out, right? What is the output value? I can read it out. Let us try that. So if I use, I have to see what is the hexadecimal value, right? So how many bits are here? There are 16 bits, right? I can either use a binary representation, or I can also show you the hexadecimal output by using, let's say, an hex display, right? This will be a better choice, right? And let us try to split this into 4 parts, right? So let us use a splitter. Let us use a splitter. So the bit width is 16, the output is 16 bits, and we want 4 splits, right? Because I want to show it using 4 7-segment LEDs. Okay, so now let us yeah, so we can use something like this, and we are going to have 4 of them. So 1 2 3 4. So these are the 4 7-segment LEDs that are going to typically show you your control watt value. Okay, so this is going to be the most significant bit, let's say 12 to 15. I can put these things a little bit down. This is going to be the most significant, the way we read it. This is going to be the second most significant. This is going to be the third most significant, and this is going to be the fourth one. Okay, so let us see. It has to be enabled, and what are the other things that are there we need to see. So if we issue an address, so what is the issue here? We have to see there is no okay, bit width is 16. Hopefully this is okay. I'm not sure, because sometimes there are some issues with the bits. So our address lookup is going to be having 7 bits, right? So this is 7, and this is the thing that we want to use for looking up the address, right? So this would be 7 bits, and once we issue some value as an address, right, the corresponding control word is going to be visible. So what you are seeing here, I can annotate that. Just look into annotation. So this is your micro instruction. Okay, so this is your micro instruction, and the thing that we are doing here is your address, which is nothing but opcode 4 bits plus T state 3 bits. Okay. So this is your T state, which is going to give you 3 bits. The last 3 bits, 100 is your T state, 0001 is your 0001 is your opcode. Okay. So 100 they might not have anything. So maybe let us do 000. If I do 000 for any instruction, don't care about this 1, 2, 3 and 4. So we don't care about it, right? So any instruction, we have 5 instructions. So let's say for any instruction, if I have 000 as the last 3 bits, right, it is always going to be 2080. Why it is 2080? This is basically the first micro instruction of your any instruction, the fetch cycle. If you do 001, it is going to be 4600. Doesn't matter if you, even if you do, let's say for another instruction, let's say 001, this is another instruction, right? So 000, the last 3 bits are going to be always 2080. 001 is going to be 4600, right? And we programmed it, right? You can just remove the new line for better readability, and you can see that, right? 2080 is going to be the 0th micro instruction. 4600 is the first micro instruction. Doesn't matter which instruction it is, right? For other instructions, I could see that there is a 0180, right? 0180 is probably referring to the memory, right? We have LDA, STA and addition and subtraction. It is referring to the memory. So irrespective of whether it is addition or subtraction, LDA, STA, you have to load the memory address register from the instruction register, right? So that is going to result in 0180. How it is resulting in 0180, we have discussed it many times, right? In the slides in the previous sessions, it is there. Please check it out. So let us try to see if it is last 3 digits is 010, it is going to be 0180. Okay. So this is nothing but control signals. So these control signals are going to be fed to the CPU, right? If you actually have a huge, here I can actually split it into different elements, right? The output, I can use a splitter, right? If you have to use a real, if you want to, once you implement it, right, you have to implement it using this kind of a splitter, so that it takes a bus and it splits it into individual bits, right? So you enter bit width is 16 and the bit split will be 1 1 1 1 4 5 6 7 8 9 10 11 12 13 14 15 16, right? If you do this, you have this gigantic line, right? This is nothing but your control bus which goes to the CPU, right? Now you can simply put these values, and these are the things that actually goes out to the CPU. Okay, so these are basically, I'm not extending it. This is just going to the CPU, and there are different meanings to this, right? As you remember now, some of these lines are register A in, some of these the lines could mean register B out, ALU out, PC increment and so on. There, all the thing has been encoded in the terms of micro instructions inside the EEPROM, right? So now you don't have to worry about it. So here you basically have to provide the address, and this address is going to come from where? This is not manually issued, right? This is also going to come from the processor. The processor's instruction register is going to tell the control logic. So this is your control logic, the software ROM. What is the micro instruction? What is the instruction that is getting executed, right? So what you need here is the let us delete this, right? What you need here is basically the the instruction input that comes from the processor and a counter, right? So in our case, let us use a default counter that is available here, but you need to typically use a ring counter. Okay, so I can use a ready-made, I think there is an available counter here in this simulator, right? So this is a counter and this is going to require a clock. So we will use a clock here. So, and I can also specify the maximum value of the bit width, right? So this bit width could be, instead of 8, we are going to use a T state counter that has 3 bits, right? We are only interested in counting from 0 to 5, right? So we should use a 3-bit counter and not a 8-bit counter. And so this is your 3-bit output, and this is going to go from 0 to 7, right? Let us do the very naive thing first, and then we are going to make it max it by some other value. Okay, so this is your 3-bit bus, right? And you also have to give an instruction input, right, that comes from the processor. So this is our this is the processor side rather, which gives you the instruction, right? So it's a 4-bit for us. This also travels inside the control logic, and we have to merge them, right? So we again use a splitter. So this is 3 bits and this is 4 bits, totally 7 bits. So you have 7 bits split into 4 and 3. Okay, so 0 to 3 is the least significant part, right? Let me rotate it. Sorry. So this is your address. So this is your least significant 3 bits, that is your counter. Hopefully this is okay. I think I made a mistake. So 4 to 6 is 3 bits. So I have to do the other way around. So I have to make the splitter 7 instead of 4. I have to do 3 4, I guess. So if I do 3 4 0 to 2, yeah. So these are the 3 bits. So this is your least significant 3 bits, and this is your most significant 4 bits. So it is 7 bits. So now you can see that with the clock for any instruction, so 0000 is the instruction that is coming from the processor, right? And let me show you the boundaries just to be on the annotation, right? So this is a rectangle. So everything that is happening here, right, that actually goes to your processor. So this entire yellow part, or rather I would say that this is our control logic, the yellow box. So the yellow box is not the clock is from outside. Okay. This entire thing becomes the control logic. Okay. So this is an input coming from the processor to the control board. So this is an input, as you can see. This is going to come from the instruction register. This 0000 depends on what is your instruction. It is going to come from the control from the instruction register, and the instruction register is this 4 bits only, right? Not the data, not the address. The most significant 4 bits of the instruction is going to be the opcode. This is going to come into it. So these are the 4 bits, 6, 5, 4 and 3, that is why 3.6, and 0 to 2 is basically the least significant 3 bits. So this is coming from the counter, right? This could be ideally be a ring counter. Okay, or it could be here, as we are not using a ring counter in this particular case, we are using a simple 3-bit counter, right? And this is counting from 0 to 7. So let us see if I am using some other instruction. This is 0000 is our instruction. If I use, let's say add, right? So add is 0011. So 0011. So these are the 5 different micro instructions it is going to go through, right? And then there will be 3 zeros. So if we look at add, this is your add instruction, right? This one is your add instruction. So this is going to be 2080 4600 is for fetch, 0180 is for loading the memory, getting the content from the memory and loading it, I think, to register B. And then there are a few things for addition and then transferring the data to register A from the ALU. Okay, so these are the 5 things that it has to go through. After that, if I am using a counter that counts from 0 to 7, there will be 3 successive zeros. So let us now look at this. So our add was 0 0 1 1. Okay, so let us see. So 0 is 2080, 4600, 0180, 410 and 40. Then there are 3 zeros. Okay, what we can do, we can make the counter reset to reset at the value 5. Okay, or you can give the maximum value is 4. So then it is going to be not going to 5 anymore, it is going to go back to 0. So the total time, now you can see the total time the clock goes from 0 to 7 in this particular case is the time taken by the processor to execute the add instruction, because all these things has to happen, then only add is going to be done, right? So if I want to make it a bit smarter, I will basically, so maybe I'll put these things, right, so that you can appreciate that different lines are turning on. Some of them might be useful, some of them are not useful in all instructions, but here let us look at this. So you have all the 16 different control lines, and you can see some of them are turned on, turned off based on what it is going to do. I think in this thing we have a maximum value also. This maximum value we can specify. I think we can specify using this input. So our maximum value is going to be also 3 bits, right? And the value can be, let's say, 100, right? And then it is not going to see, after 0040 it went to 2800, so 2080, right? I can make it faster. So this is how your control signals are going to look like for addition. Okay, so 0011 is addition, so it is basically doing all the steps that are required for addition. Okay, so all these lines have meanings, right? I have associated some meanings to these lines, if you remember, right? So for example, program counter, increment, and so on. So if you look at this line, which was the topmost value, right? So if you look at our assignments, PCINC was 14. So this is the topmost line. The 15th one or the 16th one rather is not used, it's always 0, right? We are not going to look at the 16th line. So if you see that complete cycle after it is over, only this line is glowing, right? That means that after you finish the entire operation, then you increment the program counter. So this program counter inc is going to be on once per the entire execution of the micro instruction. Okay, so if I make it some other instruction, let's say 0001, the pattern is going to be different. If I want to make it 0010, this is something else, this is going to be different. Okay, so this is how you implement the control logic, at least in software, right? Software, I mean, this basically a software control logic which contains the micro instructions in the EEPROM. Okay, hope you can create it for any other instruction that you want to implement, right?